All right, good morning, everyone. We have two awesome students who have signed up at 10 a.m. on a Saturday morning. Thank you very much. What we're going to do today is, besides having Freddie distract us in the background because he is bored out of his mind because I won't play chess with him, we are going to talk about dilations to get you set for your test. I think almost everything in here I found on your test. I just noticed one question that I think I might have missed. So as time is left, I will add on that. I think people, Freddie, are just going to watch these videos to watch what a silly goose you are. Anyway. All right, so let's take a look. So these are the standards that are going to be on your test. We have AKS 16, 17, 18, 19, and 20. So 16, real quick, is going to talk about things like verifying properties of dilations. Okay, excuse me. I'm at enough. Okay, properties of dilations, meaning like what is the center of dilation, what is the scale factor. So remembering how to do those components. This next piece, which is why I'm showing you what the actual AKS is really going to help you because it's actually a question on your test. So some things that other to know is a dilation takes a line not passing through the center and it creates a parallel line and leaves the line passing through the center unchanged. Okay. Second, a dilation of a line segment is longer or shorter given the scale factor. But the main thing is that whenever you dilate things, you're creating parallel lines. So if my hand is dilated, these lines are parallel. Always creates the parallel lines. Next, given two figures, use the definition of similarity to in terms of Similarity Transformations to decide if they're similar. So we're going to explain Similarity Transformations by this part right here, corresponding pairs of angles and the proportionality of corresponding pairs of sides. That's when we come into the main things I tell you when it comes to are they similar. Again, if they're similar, the sides are proportional. And we usually say the angles are the same, but let's lift our math language and we'll just say that the angles are congruent because we know that angles and same and congruent are the same. So that is the main takeaway there. So looking at the shapes, if the angles measures are the same, if they're the congruent, that's what matters. Next, we need to know things like using properties of similarity, including angle. And then coming down, we're going to talk more about not only angle, but we've also talked that there is also side angle side proportionality. I'm meaning if the sides are proportional and the angle is congruent, then we can do side angle side to prove they're similar. And then also we have that, why did I just blank? Angle, side, angle. Same idea. Or not angle, side, side. Again, so if all three sides are proportional, then we know that they also have to be similar if they have the same scale factor. AKS 19 talks again, if one line is parallel to one side, it divides it proportionally. And we've kind of talked about that just setting up, like if this was 3 and this was 7 and this was 2 and we had to find x, we would do 3 over 7 equals 2 over x and cross multiply. We'll talk about that. And then the last one is just understanding a little bit about proofs. I do not believe this test has a proof on it because I'm changing the test up a little bit. So that's kind of what you can expect to be on the test. Moving on, I'm going to pretend I never taught you about dilations because it's been a minute. So some of this might be a review for you. Remember dilations in the coordinate plane. The center of dilation is the origin if it doesn't tell you. If it tells you where there's a center of dilation, like I'm going to show you several problems where the center of dilation is not the origin. So there are times when that's the case. But if it doesn't tell you, you can assume if it's on the coordinate plane, the center of dilation is the origin. Then we find the new coordinates by multiplying by the scale factor. And then the big takeaway here is unlike the other three transformations, rotations, reflections, and translations, dilations are not isometric, meaning that size is not preserved. Again, the sides are proportional. That's the main thing. Not equivalent, but proportional. The only time that the sides would be the same is when you have a scale factor. Remember, K represents scale factor of 1, because any number times 1 is itself. So we started this unit off by doing a Kahoot, and the Kahoot you were deciding, is it proportional? Is it an enlargement or is it a reduction? Enlargements are anything that the scale factor is greater than 1. And reductions are anything the scale factor is less than 1. Now, sometimes kids get a little caught up. They think that you can multiply by a negative. You can never have a negative dilation. That would be like you took a shape and it like went into a black hole and came out the other side. It's not possible, or at least in 10th grade geometry, it's not possible. So we would never have a scale factor of -1. So how could you find scale factor? Here is an example of how to do it. One is we've always looked at the sides. So like we've taken, okay, what's P of R? And we've said new over old. And when we say new over old, we know that really the math language is to take the image divided by the pre-image. But what's interesting is that there's a lot of lines that we can pick, because just like the sides remain parallel and proportional, so do the measures of the lines that go to each of it from the center of dilation. So let me show you an example. If we look here in this picture, we can see that the distance from C, the center of dilation, to P is 3. So instead of doing it like P prime R prime over PR, you can also do it by like the distance between the center of dilation and a point. And again, remember the image is always going to be in the top and the pre-image is always going to be in the bottom, or the prime will always be on the top and the one that doesn't have the prime would always be in the bottom. So here for the enlargement, it was the new shape, the distance between the center of dilation to the point was 5, and the distance from the center of dilation to the original image was 3, so the dilation factor was 5/3. And the other one, they started with the red triangle as the first shape, and then it went down to the smaller triangle. And again, they're just measuring the distance. So you can, if you don't have the lengths of the sides, you might have the measurement from the center of dilation to the point, and it has the exact same effect to determine what the scale factor is. So let's take a look here. It says, the outer triangle is a dilation image of the inside triangle. Describe the dilation. So let's think about a couple things that we know about dilation. Now, technically speaking, we know that anytime that we have a dilation and they don't give us a center of dilation, we know the center of dilation is going to be the origin. But in this case, let's prove it. I switched over to, hopefully it'll work, PowerPoint, so we can draw lines. So if I take my line right here and I bring this down, the way that we find the center of dilation is we connect our points. So I'm going to connect B and B prime and see where it ends up pointing to. Okay, then I can do the same thing again. Whoops. And this time I will connect C and C prime and see what happens. And then if I need to do it one more time, just because I don't believe myself, I will connect A and A prime and extend the lines on as far as I can. And we can see that all three of those lines, when I connect A and A prime, B and B prime, C and C prime, they all connect to the origin. So that proves that in this case, the center of dilation is the origin. Let's get those lines off so we have space to work. So then it says, describe the dilation that happened. Okay, so this is not necessarily an exact science, because these are, the slopes are kind of bizarro, but there's a couple ways that you can do it. One of the ways that we talked about is finding what the image is, what the pre-image is, and dividing. So for example, if I have point A is right here, that started at -2, -2. I'm sorry, I'm going to teach this with the vector movement. So we're going to do this by vectors. So we know our center of dilation is the origin. So when I talk about vectors, remember vectors are like translations. So even though technically in this case, because what I'm talking about is specifically from the origin, so technically speaking, the point and the vector is the same. The difference is I'm going to put the little brackets instead. So we know that point A is -2 for the x and 2 for the y. So from 0, I had to go left 2 and down 2. Or in this case, I guess this is your left and then down. However, when I have my A prime point and I find my vector, this is at 4, -4, or -4, -4. Oops. So really, when I'm trying to find what was that dilation or scale factor, this is our image. The cool thing is the middle part. All we need to do to find the scale factor is just divide one of these numbers by the other. So to find my scale factor, I'm just going to divide my image, -4, by my image, -2, and get a positive scale factor of 2. Now, I don't have to do that for every single one of the points because it tells me that it's a dilation. So I don't have to think that it's skewed. If something was skewed, that means that one point got dilated and the other points didn't get dilated. But in this case, everything got dilated because it told me it was a dilation. So I could stop here. I, of course, am not going to stop here just so that you guys get more practice. So if we think about B, what would I put down for B? What would be the vector for B? And I'll wait a couple seconds. And then if you guys don't respond, then I will, do it for you. But what would be the vector for B? And then we also need the vector for B prime. So if I'm right here and I'm going to B, I know I have to go left -1 and up 2. I got -2, 2. Nope, I got -1, right? So this is going to be -1, but your coordinate 2 is correct. Got it. For B prime, what would our vector be? Excellent. Our vector would be -2, +4. So again, I can pick any of the matching pairs, the x divided by the x or the y divided by the y, as long as I'm consistent in doing the image divided by the pre-image. So this case, I'm going to change it up. I'm going to do 4 divided by 2. +4 divided by +2, again, gives me the 2 vector. So we'll skip C and let's look at reductions. Now this one's a little bit different. In this case, we're still doing scale factor, but look at the center of dilation is in a different place. Let's map out where the center of dilation is. So I'm going to switch over. Let's get myself another line. So right away, I can tell just by looking at this that E and E prime are literally right on top of each other. So the fact that the E and E prime are right on top of each other is enough to tell me that my center of dilation has to be -2, -2. And if you forgot, you can just write that down. When the image and pre-image are the same point, then it's a center of dilation. The center of dilation. Center of dilation. So when the image and pre-image are the same point, then that's the center of dilation. Now, we could prove it again. To prove it, all we're going to do is E obviously will just be E. I could do this and see that F and F prime are going to match up and go right to that point. If I connect G and G prime, I can see again that it maps to that point. And then if I have H and H prime and connect those two and extend the line, then that happens yet again. So that is just another way to show that, yep, indeed, E and E prime are the same. So that's why it's that. Let's leave those there for fun. Yeah, that's fine. Okay, so now we're going to do vectors again. Remember, vectors are distances from our center of dilation. So since our center of dilation, our COD, is at -2, -2. So anytime we're doing our vectors, we're always doing it from the distance from -2, -2. So we know that we have E, F, G, and H. So let's take a look there. Well, we know E is already -2, -2. Okay, what's the value of F? So someone go ahead, give it me F, G, and H. Well, I keep writing our next part. Oops. I messed that up. E is going to be 0, 0 because we're doing vectors. I still keep forgetting. So what are our vectors going to be to get to F, G, and H? It's a trick question because this one's a little bit harder. Okay, what we need to do is we need to count distance from the point. So if I think of E, this point right here, how do I get from this point up to here? Well, I know that I'm not moving left or right at all. The x-coordinate is staying the same. So because the x-coordinate is staying the same to get from E to F, that means that my x-coordinate is, my x vector value is going to be 0 because I did not move left or right. However, when I go here, if I don't go left or right at all, I still go up 6 boxes. So that means my y vector is going to be 6. Next, here I've got G and G prime. Well, how do I get from E to G? Well, E is at -2. G, the x value, is at +2. So I know to get from -2 to +2, I'm going to add 4. Now I have to think about what's my y difference to get from here, my center, to up here. So if I say go 4 to the right, now I need to tell them to go 6 up, and that's the way that they would go. H, all they need to do for H is go 4 to the right, 1, 2, 3, 4, but then they're already at H. They don't have to go up and down at all. So this would be 4, 0. Okay, now let's look at our primes. Our primes are going to be done pretty much the same way. Again, we're doing everything from this center of dilation. So if I have E prime and E are the same. So when I try to find my scale factor, I wouldn't do 0 over 0 because it's going to be like undefined. So that's not going to help me. Let's look at the next one. Here's remember our here's our image. F, for me to get from E to F, I need to go over 0 and up 3, 1, 2, 3. For me to get to G prime, here's G prime, I'm going left or right 2 and up 1, 2, 3. So I'm going to write 2, 3 as my vector. And then to get to H prime, all I need to do is go over 2 and not do anything else. So again, for the division part, let's ignore anything that's got a 0, okay? Because that really wouldn't help us because we're going to pretty much just be doing divided by 0, divided by 0. So here, let's take a look. Here I have a 6, here I have a 3, so that could work. These could work, or these could work. Any of these pairings could work because it's a number divided by a number. It's a natural number divided by a natural number. So again, our scale factor is always our image value divided by our pre-image. Yep, and actually I am doing it way more than I need to do it. I only needed to do it for 1 point. So really, I could have just done it for G and G prime and been done with the problem. So the question was, so you do this when you want to find the scale factor. Yeah, the whole thing I'm showing you is how to find scale factor, but you also can do this process, which we're going to see when you're given the scale factor and you need to find the image. So I'm giving you way more. So I'll finish explaining this slide, and actually let me copy this slide, and then I'll show you what I would actually have done on the test, because I'm giving you way more information than you need. So let me delete that. And so I'll go back and show it to you, how I would have done it on the test. But yes, right now we're just doing, when we have the pre-image and we have the image, what do we need to do to find the scale factor? But I'll show you the much faster way. But right now I'm just explaining it the vector way. So again, we've got image over pre-image. So we're just going to do our division of 3 over 6, which gives us a scale factor of 1/2. Okay. So on the test, if I had this question and it asked me to determine the scale factor based on this, I would never pick E. I mean, I could technically pick F or H. What you could have done here is you could have just done 6 over 3. I'm sorry, 6 and 3, and you could have immediately just done 3 over 6 and gotten 1/2. That's one way to do it. You could have done it by distances in this problem, because in this problem, it's nice and even. It's very easy to count 1, 2, 3, and 1, 2, 3, 4, 5, 6. In this problem, though, it's not as easy to do that because, because it doesn't line up perfectly. None of these points I can easily count how long is it from A to B. I can't count that. So that's why we have to look at the point values. And when we look at the point values, again, you find your center of dilation and you just do it for one thing. So this is our center of dilation. Here's our COD. So our B is -1, +2. Our B prime is -2, 4 from our center of dilation. So then I would just do 4 over 2 and get 2. So on the test, it's literally a lot. I wouldn't do every single point. I'm just showing you every single point to remind you how to do vectors. That's it. Okay. Next, finding the center of dilation. We kind of already talked about this before. Anytime, so you can do new over old for every dilation around the origin. Yes, you can do new over old for every dilation around the origin. And you also do it with vectors. The only reason why you really should use vectors is when your center of dilation is not the origin, because that changes how far the distance is. So if we look here in this picture here, if I look here, from this point right here, I would say E and E prime is both, let's say, 2 over 2. Like if I had my center of dilation here, my my vector would be -2, -2. And my E prime, my vector would still be -2 over -2. So then when I do that, I get a scale factor of 1. But if I look at G and G prime, my G is 2, 4, and my G prime would be 0, 1. And then here, first of all, this 1, 1 would tell me that 0 would be my scale factor. And here I'd have a scale factor of 1/4. So you can't just do the distance divided if the center of dilation is not the origin. So when the center of dilation is not the origin, it's not as easy as just being like, oh, I could do new over old. That's when you have to get into vectors and count, okay, how many spaces is it from the center of dilation to the original, center of dilation to the image, and then from there you can do it. But you would always have to do the center of dilation, not the origin. Okay. Here, this was just one more reminder about how to draw or how to find the center of dilation. Pretty much all you do is draw a line, I don't know why yellow seems to be their favorite color today. And then you connect the points. So if I'm looking here, I know that this point is my D. Okay. And I would say this point right here. Oh, come on, pen. This point would match here. And the bottom points would match here. So then I can take my line and connect the points and see what happens. So when I go like this, I can see that I made rather big marks, but we can see that all of them kind of line up to O. And again, you want to make sure that you always have at least 2 lines drawn, because without 2 lines drawn, you wouldn't end up getting the X. You need to have the X when you connect points to find the center of dilation. All right, let's look at some interesting center of dilations. Not interesting, but there's basically 3 different ways you can see it. 1, the center of the dilation could be inside the shape. 1, the center of dilation could be on the shape. And the third one, the center of dilation could be outside the shape. If you remember, if you're one of my students, we did an activity where we had to use rulers and we were drawing lines with the rulers. This was about 2.5 weeks ago. And you're basically just, or no, it was only 2 weeks ago, drawing lines and connecting and seeing how they matched up. So that was the activity I did to teach you this. This just shows you the difference between an enlargement and a reduction in each case. So I will outline ABC in yellow. So we can see that when the center of dilation is inside, it gets smaller from that point. Here's ABC with the reduction going out. Here's my original, and we can see the enlargement. Oh, why am I saying that? Yeah, I guess I didn't match it up the whole time. Here's another example with A being on it. Okay, so in this case, B would be our center of dilation in this bottom one. And then sometimes center of dilations are outside, like in this case, point O would be the center of dilation. And so those are just different examples, but we've talked about that in class already. All right, moving on. Dilations alone might not be enough to prove 2 subsimilar. Oh goodness, I just realized. So now again, the other site was from, I think, Effingham Schools. This is from, I believe his name is Mr. DeRose, or I have it somewhere on one of these slides, his name. So I just thought this was really interesting. The other thing you have to remember is dilations don't always happen beautifully. Sometimes you actually have to mix transformations. So you might have dilation, but you might also have a rotation, a reflection, or a translation. So let's look here. Dilations alone might not be enough to prove that 2 shapes are similar. Oftentimes you'll need to perform a rotation or reflection before you do your dilation. Pay close attention to the orientation and coordinate points of the corresponding shapes when you try to determine the sequence of rigid motions. So let's take a look here. I'm going to, one of the strategies I showed you, I think 2 days ago, was doing your shapes with the same, or doing your vertices with the same shape. So let's look at A. Around A, I'm going to put a circle, and then I'm going to put a circle around A prime and a circle around A double prime. Then I'm going to put a triangle around B, a triangle around B, and a triangle around B double prime. So it says to dilate from quadrilateral ABCD to either one of those, there needs to be a sequence of rigid motions first and then dilations. So let's first take a look at going from A to A prime. So going from A starts at -6, +5. And A prime was 2, -6. So we have to see, okay, well, what happened? Well, let's look at the other thing that happened. See how here the pink is on the top and the blue, or pink is on the left, the blue is on the bottom? Well, for it to get over here, we can tell that it had to have rotated. and it had to have rotated because it's kind of like my mouse is here and my hand is here. So when I rotate it, I should need to do it in reverse. Here's the mouse, here's my hand. So when I rotate it, there we go. The pink goes on the top. The mouse is on the top. So when we look at it, in order for the pink to be on the top, we have to rotate it a 90-degree turn. And we know that that 90-degree turn is going clockwise. So I would actually write negative 90 degrees because I have to go backwards 90. Well, after I rotate it 90 degrees, then let's see where the new points would be. Well, we've done our hand gestures before, so we know that every time we rotate 90 degrees, that the points flip-flop, and also they end up having the points flip, and they also take the signs of the new quadrant. So really, I know we called this A prime, but we know that there's going to be actually a hidden A point after the rotation. So I'm going to put A star. Star is not mathematical, it's just my way of saying it. So I know if I have 6, 5, and I flip-flop, I'm going to have 5, 6. And I know that this is going to land me in that first quadrant. So now, since A was negative 6, positive 5, I'm now going to put A at positive 5, positive 6. And we're calling this A star. B is at 0, 5. So if I'm at 0, 5, I know I'm flipping it and putting myself for B would be at 5, 0. And we're going to call this B star. And then we can continue flipping here. This would go here. So then this is our intermediary. Let's see, that's 5, 1, 1, 5. So this would be our shape first. And then we know that there's some kind of center of dilation that happened. And then there was the reduction. Okay. So I'm not going to continue solving this. This is a little bit more advanced than we need. But the idea is pay attention. Did it rotate or did it flip? And if it flipped, if it was a reflection, it would be more like the other one. Because here, look at our long side is on the bottom right here. And here in our original, the long side is on the top. So it's like top, so it flipped to the bottom. The other one, it was like this, and then it turned and flipped the other way. Or I'm sorry, it started like this, and then it went this way, so we knew it was a rotation. Okay. Next, we talked about similarity before. We know that you can prove triangles similar when you have two angles. You cannot prove quadrilateral similar when you have two angles because there's two angles that you don't know. But when you have triangles, if you know two, because all triangles are 180, you can subtract and get the third. So that's how you know they're similar. Because again, anytime we have similarity, we know that our main thing is that we have our sides are proportional and our angles are congruent. So in this case, when we have 51 and 51 and 77 and 77, we know that when we subtract, these values have to be the same. That's it. Here it says if the lengths of a corresponding side are proportional, the two triangles are similar. I think you need to have more than just one side. So that one we're going to kind of leave. Here it says side angle side. This is a cool one. See how they share this angle, right? Well, now we can see here that these angles here match up. And when these angles match up, they match up because they're corresponding angles. And we know that corresponding angles are congruent. So since those match up because they're corresponding angles, that means that these have to match up because they're corresponding angles, which means that we have the angles that are similar. All right, let's take a look at some more problems here. We were just kind of looking at what's the scale factor, what's the center of dilation. We don't have to be crazy. I can just do here and here. We can tell that, I don't know, can we tell the center of dilation is the origin? I don't think so. Let's just take a look what the center of dilation would be. Let's get our line. Actually, we don't even need to know what the center of dilation is because we can just measure. Here is AB, which is 3. This is nice and easy to measure. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Because that's nice and flat, we really don't need the center of dilation. I had a brain freeze. So again, we know it's going to be a length from the image over the pre-image. So in this case, it would be 9/3, and our scale factor is 3. When you cannot easily measure the lengths, that's when we have to go to the more complicated method. But when the lengths are easily measured, you can just do new over old or the image divided by the pre-image. All right, let's take a look here. We're going to try to first find that center of dilation. It's not going to be super hard considering I had to white it out, so you can probably already see it. Okay, so here's our line. So let's just start connecting points. I'm going to put this on B prime. I'm going to rotate it so it goes on forever. I'm going to put this on C prime. I'm going to rotate this so it matches up. Oops, sugar shoots. I'm going to rotate so it matches up with C prime. There we go. And then that should be enough, but if we needed to do our last one, again, we could just have done A and A prime and seen where that had matched up. So there we go. So now that we've done that, we know that our center of dilation is right here, which is at -4, -9. And then the scale factor, this is a lovely, easy picture again. We can just pay attention to the lengths of the sides. So it's very easy. We got lucky. This is nice and easy to count across. So going across here, we've got 4 and 3, which is 7. Going across here, we have 14. And then again, it's just going to be the image divided by the pre-image for a scale factor of 2. Also notice with those lines, you can see that these lines are parallel. Like if I switch colors and try to draw C, we can see the same thing. Here is BC, here's B prime, C prime. You can see how those lines are parallel. That's the main concept whenever we do dilations, is catching those parallel sides. Here, I really liked this problem. And you might actually see it at school because I really, really like it. Shapes A, B, C, D are similar, so you can find the scale factor with both sides and points. Yep, absolutely. Again, these two pictures are super easy to find the scale factor because you can easily count the boxes. This is harder to find the scale factor because there's not like a straight line that you can easily count the boxes, and I haven't taught you the distance formula yet. So in this case, we would have to, in this case, we would have to use the points to determine the scale factor. And obviously in this picture, we'd also have to rotate it first and then use the points to find the scale factor. So it just depends on what situation we're in. So if we look here, we can see that, well, from A to B, this is 1. Let's just put some values down to get us going. So we know the measure of length. This length is 1. The measure of this length is 2. This is 2. This is 4. This is 4. This is 1, 2, 3, 4, 5, 6, 7, 8. This distance is 1, 2, 3, 4, 5, 6. And this distance is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so in this case, it was saying shapes A, B, C, D are similar, so we know that they are. Identify at least 4 dilations noting center of dilation and scale factor. So this is kind of fun. We can just kind of pick what we want to do. I can take this guy right here, and I guess I can't rotate it. Can I rotate you? Nope. So much for using that ruler. Goodbye, ruler. Let's go back to insert a line. So for example, if I'm talking C and D as my points, I'm going to draw my line, and then I'm going to connect and the corresponding point. So if I put C here, I have to say, okay, well, where is that going to match up to? It's going to match up to D over here. And then I can just extend this out forever, and then we got to try our other one. So we have that matches here. Almost having a little technical difficulty. Okay, then I can paste my line down and come up with the corresponding parts for the top 2 points. So if I map, wow. If I take my line and start it at this top point and then move my line so it goes on forever through here. Wow, this center of dilation is super far away. All the way out there would be my center of dilation for C and D. And you can kind of see how that would work. I could even do it for the last point. If I moved this right here on this right angle, and then had it go through the other right angle, you can see how they all kind of go to the point if I was, doing a much better job of connecting the different values. So that would be how you would find that. The scale factor would be super uber easy. Again, it would just be new over old. So if I'm going from C to D, then I would have to put D over C to get 6 over 4. Or 3/2 or 1.5. But if I was going from D to C, because C to D got bigger, it was an enlargement. If I'm going from D to C, then again, the image C goes over the pre-image D, in which case I'd have 4 over 6, or 2/3 is my scale factor. So again, you really want to pay attention to what is the image, what is the pre-image. Here, same idea. When we look here, if we go from G to E, we're just connecting our point. So we know that the center of dilation has to be somewhere on this line. We know that these points would correspond to each other. So I'm going to bring this guy over here, map it on this point right here, and then have it go through that same red point, and I can see that up top would be my center of dilation for that. And again, I could just do the same thing through the top corners of the points and essentially get the same result. So center of dilation, and these again are super easy. All we needed to do is just go ahead and map it. Now, I added one extra question here. Let's talk about H. The questions reads if, and that you have a question like this on your test, if rectangle H went under a dilation of 2 about the origin, what would be the length of the longest side? Now pay attention real quick. Because it says length and not coordinates, we don't have to do anything funny with vectors. And also it just tells us, in this case, the dilation is 0. But the same thing would be true if it told us that the dilation occurred, that the center of dilation was, let's say, 5, 6, like all the way over up here. It would still be the same because it's not asking us for the new coordinates. It's just asking for what's the dilation. And it told you it was a dilation of 2. So all we do is we say, okay, well, here is rectangle H. The longest side we have 2 and 3. 3 is our longest side. So the length of the image or the pre-image is 3. So all we're going to do is 3 times 2 to get 6 for the length of our other one. So no matter what our origin is, no matter what our pre-image is, all we need to do is just go ahead and multiply. You don't have to do anything with vectors because it doesn't matter where the center of dilation is. We just know it's being dilated. Now, if it asks you for the coordinates, then it would matter. But if it doesn't ask you for the coordinates, then it doesn't matter. Couple more questions. Describe the sequence of transformations that would map one to itself. Let's take a picture here. Here we have our A point. Here we have our A point. So we know there was some kind of turning that had to have happened. And then we have our C prime is down here. I'm sorry, our C and our C prime. So we can see that originally this was our line. And now we can tell that it turned. And so if it started here and it turned this way, we know that it went in a 90 degree, or actually it might even be 180. Not only did it turn, but look at, and this is where it started from, and this is where it ended up. Okay, so we have even a bigger rotation than I was thinking. Let's see, because that would not be it. So let's write our points, because that might help me get a little clearer, because all of a sudden I'm brain freezing. So our A is -7, +2, and our A prime is at 12, 0. Our B, or our C, was -5, -6, and our C prime ended at 1. I honestly can't tell from all my stuff right here. 1. Oh no, 0, 3. Okay. So if this turned, ooh, this is actually going to be a rotation and a reflection, because we have to rotate it first to get it into this way. And then, but when we rotate it 180 degrees, it's going to look like this. Stop with the laser pointer. And then we have to reflect it to bring it back down here. So we would have to do both, and then you would have your dilation from there. This is harder than what you're going to see on your test. Stop with the laser pointer, please. Okay, next, let's look at this one. Suppose A and B are parallel. Are they similar? Explain. Yes! Because AB and A prime B prime are parallel, that's like the whole point of what similarity is. And you have a question on your test where it's going to give you a shape similar to this, and you're going to have to say, like, does this part equal this part? Does this part equal this part? So those are the types of things that you're going to do. So because these lines are parallel, we're going to assume that what they told us is the truth. We know that we already have this angle because it's actually just the reflexive property. Because angle O is just going to be congruent to angle O. Okay. Here we already talked about that when we have angle B and angle B prime, we know that these are corresponding angles. So that makes those angles. And then the same would even be true over here. A and A prime are also corresponding. So because angles are congruent, we know that they're proportional. Now, the next thing that we need to do is figure out what the missing part is. Well, we can take OA and divide it by OA prime. So that's going to give me 14 over X. I'm sorry, I did that backwards. Doesn't technically matter, but I typically have taught you to, no, we can do it that way. So that's going to give us, if we do, let me start over. I want it, now that I showed, no, I don't want to do it that way. I want to copy this. I want to still leave that up in case people need the notes, but I want to have everything off except our stuff because I want to write on the triangle. Okay. So now let's match up things. So we now that we know that we have the corresponding parts and angles, let's match it. Well, it wants us to find OA. So for our purposes, we're going to call OA X. And it tells us that the length of the whole thing is 14. They also give us AB as being 5. And they give us A prime B prime as being 17.5. So really, all you need to do is just make sure you map it up. So I'm going to have the yellow triangle be my original. So I'm just going to match up 5 over matches up to 17.5. And that has to match up to X over 14. So some people I've seen when they do triangles, they do small over small equals the medium over the medium equals the large over the large. And then as long as you're just consistent that you always have, in this case, our small values would always go to the yellow triangle, and then our other ones, our denominators, would always map to the green triangle, however you want to do it. Then we just cross multiply. Hey Google, what is 14 times 5?
The answer is 70.
Hey Google, what's 70 divided by 17.5?
The answer is 4.
Thank you, Google. Now we know our X value is 4, so that would replace this part. And then it still wants us to find OB prime. So since we already know that OB is 3.2, I'm going to make this long thing be our Y. So we'll just, again, map it up. 3.2 over the whole thing Y has to equal 5 over 17.5. Hey Google, what's 17.5 times 3.2?
The answer is 56.
Hey Google, what's 56 divided by 5?
The answer is 11.2.
Okay, and then now we have our Y value. So things that we know. Well, we know that the pieces are proportional. We know that AB is parallel to A prime B prime. We know that the center of dilation would have to be O. So the question you're going to see on your test is you're going to see an image similar to this. You might have to find the missing pieces, and then you're going to click a couple of them, because it's like choose all that apply, that match up to this question. Okay, 3 more questions. Are they similar? Explain. So, and then it says find the length of YZ. Well, we already know here, this is 48, and we don't see 48 over here. So if they were similar, this would have to be 48 degrees. We don't know if it is. All we know is that the 86 matches to the 86, and we want to know, are both of these 46? So all you need to do it is just subtract. It's that simple. So we know that there's 180 degrees in a triangle. So I'm going to subtract my 86. That's going to leave me with 94. I'm going to subtract my 48, and that's going to leave me with 46 degrees. So now I know that, yep, the triangles are similar. If you had to prove it, you could prove it with angle-angle similarity. Or right now, the question is, what type of similarity would it be? We just proved it by angle-angle, because we noticed that 86 degrees is corresponding to 86. When we did our subtraction, we saw that 46 matches to 46, so that would give us angle-angle. You wouldn't yet be able to do proportional, because we don't know what the scale factor is to get 3.4 to 20.4. So we would have to have another value to compare it to make sure it's proportional for us to do, well, there isn't angle side angle anyway. So it's just side angle side proportionality. So, okay, so moving on, angle angle. Now we're just going to figure out our missing value. Now, the next thing I want to remind you to do is, I got a lot of going on. Please match up your letters. So, I guess we need to leave this. So, for example, we have X y, z. Well, angle x is 86 degrees. That matches here, so this will be x prime. Y is 46, y prime, that matches, and then our z prime. So then it wants the length of yz, which is this value right here. Yz is going to map to y prime z prime, so I'm going to do xy over x prime y prime will equal yz over y prime z prime. Now, I also could have done it the other way. I could have done x prime over y prime over xy over y prime over z prime. Or I'm sorry, y prime z prime over yz. In this case, it doesn't matter the order because we're not determining the scale factor. We're looking at proportions and cross multiplying. That's it. So here I've got just plug it in. So I've got xy was 3.4. X prime y prime was 20.4. We're trying to find yz, and y prime z prime is 25.8. Hey Google, what's 25.8 times 3.4?
The answer is 87.72.
Hey Google, what's 87.72 divided by 20.4?
The answer is 4.3.
And there we go. Now we know the length is 4.3. So again, it's just mapping and putting it on. Nothing super challenging. Okay, you will see a question like this. The coordinates of C after a dilation centered at B are 6, 4. What are the coordinates of A? So what you need to do is, okay, well, what's our center of dilation? This is our center of dilation. I intentionally picked a center of dilation that wasn't 0, 0, because I want us to look at vectors one more time because you will have a question almost exactly like this with a different picture, different numbers. So if we know our center of dilation is at B, well, B is 3, 4. That's our center of dilation. So first we're going to see, okay, what is C? Well, we're not looking at C in terms of what's the coordinates of C. We're looking at C in terms of what is the vector to get us from B to C. Well, to get us from B to C, we have 1, 2, 3, 4, 5, 6. We moved 6 spaces to the right, and we did not move up or down. Now it tells us that C prime is 6, 4. So that would mean this is where our C prime is. Well, how did we get from B to C prime? We moved 1, 2, 3. And we did not move up or down. So when I need to find my scale factor, I'm going to do new over old. So I'm going to do 3 over 6, or get a scale factor of 1/2. So I know my scale factor for A, whatever my A vector is, I'm going to multiply my A vector by 1/2 to get my new coordinates of A. Now, really, I'm going to show you an easy way. Because this one right here is easy. The picture you're going to have on your test is not going to be as easy as this, so that's why I'm showing you the longer way. You might already know a quick way, which I can show you after, but I want to show you the real way to do it because the picture on your test is not as easy as this. So the real way is, what we did first is we said, what's the vector from B to C? 6, 0. What's the vector from B to C prime? 3, 0. Divide new over old for a scale factor of 1/2. Now we're finding, okay, what's the vector for A? Well, if I'm starting at B, my vector for A is I don't go up or I don't go left or right at all, so 0, and then I go up 4. In order for me to get A prime, I have to multiply 0 by 1/2, which is 0, and 4 by 1/2, which is 2. Now, this is where they're going to try to trick you. They might have 0, 2 as an answer choice, but it would be wrong because 0, 2 represents the vector. So from B, I'm going to go left and right 0, and then I'm going to go up 2. So that means that my point of A prime is going to be right here, which is 3, 6. That's my answer. The point of A prime is 3, 6. Now, that is the real way to do this problem. The picture on your test is not easy like this one. Pretending that it was easy, even though it's not going to be on this test, but who knows, you might get a test that it's easy. Oops. All we really needed to do was, well, we know that this is our center of dilation. We know that this distance was 6. We knew that this distance right here was 3. So we could have just done 3 divided by 6 and got 1/2 as my scale factor. Then you could have said, well, my original distance is 4. What's 4 times 1/2? 2. So I have to go 1, 2. That's another way you could have done this problem. A third way you could have done this problem is you could have said, well, I don't know what distance I need here. This would be my x. So I could have just done 6 over 3 equals 4 over x and cross multiplied and got 6x equals 12 and then divide to know that this part would have had to be 2. Either way. All right, last set, flipped or twisted. So first of all, let's see what we know. Well, we know this is 70 degrees, and we know this is 70 degrees because it tells us. We know that these are vertical angles, so this has to be 30 degrees right here. That means if 70 plus 30 is 100, this would have to be 80 degrees. So in this case, we know that it was flipped. It was reflected right here. Because if I could fold my screen in half, I would then be able to see that this is my line of reflection. Here, it's a little bit different. Here, we see 80 degrees. Here, we see 80 degrees. So right away, we know that on the left triangle, the 80 degrees is on the bottom, but on the right triangle, the 80 degrees is on the top. So we know that we had a rotation of 180. The other thing we know is, technically speaking, and as a refresher, these angles are alternate interior angles. That's what makes them congruent. So then here, if this was 80, this is 30. 80 plus 30 is 110, which leaves 70 for both of these because they're alternate interior angles. So the measure of angle A is 70. The measure of angle TBM was 30 because of vertical angles. And the measure of T was 70. So then that's one refresher is it reflected or is it rotated? They could use flipped and twisted, but we know how to use proper math language. And then what's our proportion to find x? Let's see, here's x. So we know that x has to go to 10. So right away, let's just do that one. And that means that 9 would maps to 12. So that's that. You could solve it, but we don't have to. Same idea here. We know that this side, okay, we know that this side has to map here. So we would just make sure we have our 6 over y equals 9 over 12. This is a little bit different on this side. Look at where our x is. This will still map to here. So we can still do our x over 6. That's not the problem. The issue is that, see how y is 80 to 30? Like if I'm looking at the line, on left, my y, it connects the 80-degree angle with the 30-degree angle. So we have to make sure that the corresponding side matches. So that means that y has to map to 10. Okay. Actually, I shouldn't have done that. That was for the next one. Y maps to 10. Here, I would put 14 or 21 has to map to 14. How did I do this? X over 6. Nope, I would do 14 over 21. Okay, and that's because we have to see, well, this T connects the 70 and 30, so that means the mapping side has to connect the 17 and 30. Okay, that is pretty much the review I had put together for your test. If there is anything else, I'll look through the test over the next couple days, but if there's anything else, the test is Tuesday. So if there's anything else, I will record in a video Monday afternoon or Monday night. I'm not going to go through all of this stuff because people can watch this video, but we might do like a half an hour review Monday night, maybe around like 6:30, just for one more quickie to get you ready for the test. But I won't explain as much as I've explained today. But our test for ERIG is Wednesday, and I know both of you are mine. Other teachers are giving their test on Wednesday, but our test is Tuesday. All right, thank you guys for logging in on a Saturday. I hope this helped, and I hope whoever watches the videos later helps. And I will see you later. Bye.